Mount one red and one green LED closely on a circuit board. Then connect the circuit to a battery. Measure the distance between the LEDs. Now mount the circuit board on a wall. Then stand back to a distance of about 1 meter from the circuit board. You should be able to distinguish the red and the green lights clearly. Gradually move back from the lights until you see the lights become a yellow spot. Now you are no longer able to resolve the two lights separately. Note this distance of the eyes from the lights and find out the resolving power of your eyes in terms of angular resolution.
3.2 Seeing at nanoscale. Let's begin. Color display. If you come very close to the television, you can identify the tiny pixels on the screen. But if you are a few meters away, you can hardly see the pixels anymore, because your eyes are not powerful enough to resolve the smallest details on the screen. 1. Development of microscopes. Compound microscope was invented about 400 years ago, which is an optical microscope. Later on, more advanced microscopes, such as TEM and STM, allow us to see at nanoscale by increasing the resolution of the instrument. 2. The optical microscopes. A. From single lens to combined lens. A single-hand lens is a magnifying glass. Optical aberration often affects the quality of the images, especially when the magnification is high. A combined microscope can significantly increase the magnification with two convex lenses. In a combined microscope, the objective lens forms a real inverted image, and then the eyepiece magnifies the inverted image to form a final image which is magnified and inverted. With suitable choice of lenses, the magnification of a combined microscope can be further increased, but never able to distinguish details within 200 nanometers apart. Moreover, diffraction effect limits the resolution of all instruments based on wave theory. B. Diffraction-limited resolution. When light passes through an aperture, which is an opening, diffraction occurs. A single dot will produce a diffraction pattern which appears as concentric circles of alternate bright and dark rings. And what if there are two dots very close to each other? Each will have its own diffraction pattern. When the two patterns overlap, it would be harder to tell there are two dots. Their diffraction patterns will overlap, and the two objects are not resolved. The size of the aperture and the angular separation between the objects determine whether the objects can be resolved. For a larger aperture, there will be less diffraction effect, and it will be easier to resolve the objects. When the angular separation is smaller, there will be more overlapping of the diffraction pattern, and that will be harder to resolve the objects. The Rayling's criterion defines the condition at which the two close objects can just be distinguished, which states that the central maximum of the diffraction pattern of one just overlap the first order minimum of the other. And yet, even under such condition, there is a way to resolve the two objects. It is by decreasing the wavelength. So what does that mean? Let's take a look at checkpoint 4 below. Part A. The central maximum of the green diffraction pattern is just inside the first order minimum of the red one, and so the 2-point objects are not resolved. In Part B, the central maximum of the green diffraction pattern is just outside the first order minimum of the red one, and so the 2-point objects are resolved. When Wayling's criterion is expressed mathematically, it states that theta r is approximately equal to 1.22 lambda over d, where the minimum resolving angle theta r is measured in radians. Theta r is called the angular resolution of the microscope. Note that the words resolution and angular resolution have different meanings. A microscope with higher resolution has a smaller angular resolution, theta r. Example 2. The diffraction-limited vision of human eye. So, what is theta r? It is the angle subtends between the objects at the observer eye. Let's look at figure A below. So, a smaller angle means the two objects can be closer, and still we can distinguish them. From the expression theta r approximately equal to 1.22 lambda over d, you can see a larger diameter d or a shorter wavelength lambda can reduce diffraction effect and hence reducing the angular resolution theta r, and so improving the resolution of the microscope. Example 3. In Part A, you can see how distance L may affect the angular resolution. In Part B, the aperture diameter d is changed. It also affects the angular resolution and hence the appearance of the picture. Spend a few minutes to read the solution carefully. Do check point 5 on the next page.